This is the promised and long-awaited ShowMe about simplifying radicals. The property we're going to use most in simplifying radicals is the property that allows us to factor a radicand. The radicand is the number inside the radical. If we can factor it, especially if we can factor it a certain way, we can simplify things. The first rule to simplifying radicals is that if I have a product under a radical, I can break it down into the product of two radicals, each one holding a factor of the original radicand. Here's how that helps us. Here we've got the square root of 245. We can factor that many ways. There are lots of ways to break it up. The one that helps us most, however, is the square root of 49 times 5. And the reason that helps us most is the square root of 49 can actually be simplified. The square root of 49 is 7. So we can rewrite the square root of 245 as 7 square roots of 5. This is something that you actually have to do. In my class, not doing that is akin to the kind of error you're making when you forget to reduce a fraction. Now, to do this, you really need to have certain numbers in your head ready to go at all times. And those numbers in particular would be the square numbers. Numbers like the ones I'm writing right now should be ready. You should be looking for them in the work that you do. And when they pop up, you should be ready to act, ready to seize the opportunity to simplify your radicals. At the very least, every student should have the numbers on the right memorized. You may need to use a calculator to generate the others, or you may be a bit of a nerd like me and go ahead and memorize the squares all the way up to 900. We can use these factoring properties on radicals that include variables as well. Consider the square root of 72x cubed. We can rewrite that as a product of several radicals. For instance, 36 is a factor of 72. And x cubed can break down into the square root of x squared times the square root of x. Of those factors, the square root of 36 and the square root of x squared can be simplified. The square root of 36 is 6, and the square root of x squared is x. The square root of 2 and the square root of x, however, we cannot be sure that x is a square number, and we know that 2 isn't. So those numbers stay under the radical. As a result, the simplification of the square root of 72x cubed is 6x times the square root of 2x. Again, if you don't do this in many teachers' classes, including my own, this is cause for marking your work down. It is important. Like I said, it's an error on the same level as forgetting to reduce fractions to lowest terms. You need to reduce your radicals whenever you can. Simplifying radicals also comes into play when you multiply two irrational numbers of the type shown here. 14 has no square factors. 6 has no square factors. But what happens if we multiply them together? Well, 14 times 6 is 84. 84 has a square factor. 84 is equal to 4 times 21. So I can break the square root of 84 up into the square root of 4 times the square root of 21. The square root of 4 is 2, so the final result is 2 square roots of 21. Now there's another way to look at this problem. I like doing it this way myself. Whenever I see a product involving square roots that might be factorable, I go ahead and factor the square roots before I multiply. I don't want to take a chance on having to deal with numbers so large I may not be able to do anything with them. The square root of 2 and the square root of 2, we know what their product is going to be. By definition, the square root of 2 times itself has to be 2. And then the square root of 7 and the square root of 3 aren't going to be able to get out of the situation. They'll have to go together into the same radical. Notice we get the same result either way. As far as my own students are concerned, I don't care how you do it, but I just think that this second way is a little bit better because you don't end up dealing with larger numbers. And while 84 doesn't really intimidate me that much anymore, I've still got some students where if they see 84, they're not sure where to go factoring. You won't spend a lot of time factoring 84 in most math classes these days. You don't have to factor 84 if you do it the second way. Well, after all we've done this year with multiplication and division, and realizing that they are basically different instances of the same operation, it should be no surprise to discover that if you can take a product under a radical and break it up, you can also take a quotient and do the same thing. And you can. So if we have something like the square root of 7/16, we can rewrite that as this one square root divided by another. That's awfully convenient because while the square root of 7 isn't going to simplify, the square root of 16 does. And this is actually the square root of 7 over 4. By rule, it is inappropriate to leave a fraction under a radical. So whenever you see one of these, you've got to do something with it. You cannot leave a fraction under the radical. And your first step is to rewrite it as a quotient of two radicals. Then you're not done. You do have to deal with what's on the bottom. In this case, it was easy because it happened to be a nice, neat square root. But it won't always be. Of course, we should be able to deal with variables in these situations. Just as in the previous example, the square root of a quotient is the quotient of two square roots. I have the square root of 81 over the square root of c to the 6th. Well, the square root of 81 we know is 9. As far as c to the 6th is concerned, think about this. C cubed times c cubed is c to the 6th. And that means that c cubed must be the square root of c to the 6th, because we get c to the 6th by multiplying c cubed by itself. Whenever that happens, you get a square root. So the square root of c to the 6th is c cubed. Remember, you cannot leave a fraction under a radical, and you cannot leave a radical in the denominator of a fraction. So there's much work to be done as long as either circumstance is happening. Now let's consider this quotient. A lot of work to be done here. The first step remains. Break it up into two radicals, a numerator and a denominator. At this point, we have some options. I think the best option is to factor everything on top and the bottom as much as you can. So the square root of 18 becomes the square root of 9 times the square root of 2 times the square root of x to the 4th. On the bottom, I see the square root of 4 and the square root of 2 and the square root of 3 and the square root of x. Well, let's see. On top, the square root of 9 is 3. The square root of 2 on top is going to cancel with the square root of 2 on the bottom. So those won't appear again. As far as x to the 4th is concerned, we can divide out the x on the bottom, turn the 4 into a 3, and then refactor square root of x cubed into the square root of x squared times the square root of x. On the bottom, still have the square root of 4, which is 2, and the square root of 3. Well, 3 divided by the square root of 3, by definition, think about it now, the square root of 3 times the square root of 3 has to be 3. So 3 divided by the square root of 3 has to be the square root of 3. So when these two cancel, the square root of 3 is left on top as a factor. The square root of x squared is just x. So, on top, we have x outside the radical, and 3x inside the radical. On the bottom, we just have 2. A lot of work to be done there. Perhaps there were more efficient ways to do it. I'm actually going to go back and do that one again. I think I see a better way to approach it. Perhaps we should have reduced some fractions before we began splitting things up this time. After all, 18 and 24 have a greatest common factor of 6. We can rewrite that fraction right off the bat as 3 over 4. Also, x to the 4th over x can be rewritten as just x cubed on top. That's going to make things a lot easier, I think. Now let's split it up into two radicals. We have the square root of 3x cubed on top and the square root of 4 on the bottom. Well, on top, we can at least break up 3x cubed into x squared times 3x. On the bottom, the square root of 4 is 2. As before, the square root of x squared can be turned into x, but the 3 and the x are stuck under the radical. We get the same answer, but it's a lot cleaner work. I guess the lesson there is if you can reduce the fraction right away, do it before you split the radical. As I said before, it's inappropriate to leave a fraction under a radical. It's inappropriate also to leave a radical in the denominator of a fraction. When you have a situation like this, you've got to get rid of that square root of 7. It's got to be cleared. The only way to do that without messing up the value of the number you're dealing with is to multiply by 1. But you have to pick the right version of 1. There are lots of 1s out there. There's 1. There's 2 over 2. There's pi over pi. Those are all very nice, but none of them will help us here. I've got to pick just the right version of 1. And just the right version of 1 is the one that will turn this irrational number into a rational number. That's why this is called rationalizing the denominator. Because we're taking an irrational denominator and turning it into a rational one. The best number to choose for this is the number itself. If I end up somehow taking square root of 7 times itself, I'll get 7 on the bottom. That's a rational number. Mission accomplished. But how do I multiply the bottom of this fraction by 7, and by square root of 7, and change it into 7, and still leave the value the same? Well, the answer is whatever I multiply by the bottom, I've got to multiply by the top. This is 1. It's a very odd-looking version of 1, but it's no better or worse than these other versions of 1. It's better for us right now because it's the one version of 1 that will quickly and simply rationalize that denominator. Well, we already know what happens on the denominator. 8 times the square root of 7 is, surprisingly enough, 8 square roots of 7. It seems like a simple enough change, and the question might be asked, gosh, this almost seems more complicated than what we started with. Maybe so. But rules are rules, and in the math club, we don't leave radicals in the denominator. We do not do that. Final example of this ShowMe. We've got to rationalize this denominator too. Well, we learned in the last slide, we rationalize denominators by multiplying by 1. Which version of 1 should we choose? Whichever one will take care of the bottom most simply. In this case, that would be square root of 3n. It needs to be both the numerator and the denominator. That way, we're just multiplying by 1. The value of the result is the same as the value of what we started with, but the appearances will be different. On top, 13 times 3n produces the square root of 39n. And as large as that number is, and as complicated as it might look, that doesn't reduce. There are no square factors of 39. On the bottom, when you multiply the square root of the same number by itself, you get the number. In this case, 3n. Be careful. It would be tempting here to try to reduce the 39 and the 3, or the n and the n, but you can't. As long as that radical sign is there, this is done. I hope that clears up some of the issues you're having with simplifying radicals. There'll be other ShowMes about this, and there's some other ways to rationalize denominators and other situations we have to deal with. All of them arise from solving quadratic equations or solving radical equations. We'll probably see some work on that before the school year ends too.